Welcome everybody. In the next two videos, we'll look specifically at some things related to the transfer of energy by heating processes. In this first video, we're going to look at how it's possible that we would see a different temperature change when the same amount of energy is added to or removed from different materials. Thanks for joining me. I'm Holly Mosley and I teach at Liberty High School in Frisco, Texas. So let's start with a short demonstration. In this demonstration, I have several spheres made of different materials, and you can see them, they're numbered 1 through 4. They have all been in boiling water for a really long time, so I know they've all had time to reach equilibrium with the water. So in other words, I know all the spheres are at the same temperature. I'm going to remove the spheres from the boiling water, and I'm going to place them all at the same time on a piece of paraffin. I want you to kind of think about what you expect to happen. Okay, so hopefully you've got something in mind. Let's watch the video and see what happens. So if you notice, each sphere has melted a different amount of the paraffin. They're kind of all at different depths in there. So why would that be happening? Let's think about that. So since the spheres are hotter than the paraffin, that temperature difference results in a transfer of energy to the paraffin. And that's why we see the paraffin melting. As long as there's a temperature difference between the two, so as long as those spheres are hotter than the paraffin, then that's going to keep transferring energy and that paraffin will keep melting. When that melting stops, we know there's no longer a transfer of energy, and that means that the two must be at the same temperature, so they've come to thermal equilibrium. So we know that the spheres that melt the paraffin the longest amount of time are the ones that are maintaining the higher temperature for a longer period of time, even though they're continuously transferring energy to the paraffin. So let's think about why that's happening. We already know that to change the energy of a gas, we can add or remove energy by a heating or cooling process, or by doing work on the gas. The result of that energy change is a temperature change. So temperature change is also proportional to heat and work. However, solids and liquids are incompressible, meaning they have a constant density, and we cannot do work on them by compressing them or expanding them. So that means that the temperature change of a solid or a liquid is directly proportional to the amount of energy added or removed by heating or cooling. So since temperature change is directly proportional to the energy added or removed by heating or cooling, what else matters to make that proportionality and equality? So the temperature change depends on the amount of energy added, how much of the material there is, which is the mass, and then what the object is made of. Each material has its own specific heat, which is an intrinsic property of that material determined by the arrangement of the atoms that make up that material. So let's see if we can apply what we just learned to compare the specific heats of the materials in the demonstration. I want you to pause and rank the specific heats of the materials from greatest to least. So pause real quick and see if you can come up with a ranking and a reason. Okay, because we don't know the actual temperature change or the amount of energy transferred, we can't calculate the specific heats. But we know the ones that keep melting the paraffin the longest show the smallest temperature change, because there's still a temperature difference between the sphere and the paraffin, so they keep melting the paraffin. They're continuously transferring the energy. So therefore, we can qualitatively compare the specific heats. Sphere 2, it looks like melted the furthest. In other words, it maintained a high temperature the longest, so it has the highest specific heat. Next, sphere 3, then it looks like sphere 1, and lastly, sphere 4. They're pretty close, and we probably have some energy being conducted to the air in the room as well. So what should you take away? The only way to change the internal energy, and therefore the temperature of a solid or a liquid, is to add or remove energy by a heating process. And we can actually remove the same amount of energy from different objects and observe different temperature changes if the mass of that material is different or if the type of material is different, because specific heat is an intrinsic property of the matter. So it's like density. It's based on the atomic interactions in the material. So thanks for watching. In the next video, we're going to look at the factors that affect the rate at which energy conducts through a material. See you next time. Welcome back, everybody. In this video, we're going to look at the factors that affect the rate at which energy is conducted through matter. Thanks for joining me. I'm Holly Mosley, and I teach at Liberty High School in Frisco, Texas. Let's start with a short demonstration. Here I have a couple of blocks, and I'm going to put ice cubes on each block, and we're just going to watch what happens for just a moment. So hopefully that's kind of got you thinking and trying to figure out what's going on. We're going to try to figure that out. Obviously, you can see the block on the ice cube on the left is not really melting very much. The ice cube on the right is melting very quickly. So now we're going to look at another demonstration. In this demonstration, I have several rods of the same diameter, the same length, but they're made of different materials. They extend from the central hub, and in the end of each rod, there's a little bit of paraffin, and you'll notice those are starting to melt. After 54 seconds, we have the one on rod number 1 has melted. Now we see the one on rod 5 has melted. So what I want you to focus on is the fact that these are all melting at different amounts of time. They don't all end up melting at the same time. So what we're trying to figure out is how is that related to the transfer of energy through those rods? And really what it all comes down to is it's based on the conductivity of the different materials. So each material, each of these little rods is made of a different type of metal, and each of those metals has a different conductivity. Now, the rate of energy transfer also depends on some other geometric factors that we didn't test in this experiment. So we're going to look at those as well. So the rate at which energy transferred by conduction through an object depends on the thermal conductivity of the material. And so that's what we were just looking at. That thermal conductivity is related to the arrangement of the interaction of the atoms. So it's unique to each kind of material. It's an intrinsic property, just like density, just like specific heat. So the rate at which the energy transfers depends on that thermal conductivity, but it also depends on some of the dimensions of the material. So specifically the cross-sectional area and the length of the material. And then lastly, the temperature difference between the two ends that you're trying to conduct energy from and to. So let's look at how this mathematical model fits with the atomic interactions. Here we have two objects that differ in temperature by 100 Kelvin. They're connected by a cylindrical rod through which the energy is going to be conducted from the hotter system to the colder one. So if we replace that cylindrical rod with one with a larger diameter so that the cross-sectional area is larger, the equation tells us that the more energy, we would expect more energy to be conducted through the rod in the same amount of time. In other words, the rate of energy transfer increases. But why is that? Well, that energy transfer occurs via the vibrations of those atoms and molecules. So when the cross-sectional area is large, more of those atoms and molecules can interact with each other, resulting in a greater rate of energy transfer. So a larger cross-sectional area gives more opportunities for particles to interact and transfer energy. Now let's focus on the length. We have the same setup as before, those two objects that differ by 100 Kelvin, and they're connected by a cylindrical rod. This time we're focusing in on the length of it. We're going to replace that cylindrical rod with one of length greater, with a greater length. And we know by looking at that equation that we would expect there to be less energy conducted through that rod in the same amount of time. In other words, the rate at which energy transfers will decrease. Since we know the energy is transferred via vibrations of the atoms and molecules, when there's a greater distance through which that energy has to travel, it's going to take a longer amount of time for those interactions to occur and for that energy to reach that second object. All right, lastly, let's look at the temperature difference. We have the same setup again, but this time we're going to repeat the experiment with two objects that have a greater temperature difference. Again, the equation tells us that more energy will be conducted in the same amount of time when the temperature difference is greater. So in other words, a more dramatic temperature difference results in a faster rate of energy transfer. So what should we take away from this lesson? So like specific heat or density, conductivity is an intrinsic property of matter, but it's not the same thing as specific heat. If you think back to that example with the blocks at the beginning of the video, one of those blocks was a better conductor. It was able to conduct energy from the surrounding air to that ice cube and cause it to melt faster. So the rate at which that energy transfers by conduction depends on the material, the physical dimensions of that material through which the energy is being transferred, and the temperature difference between the two locations. Thanks for watching. I'll see you again in Unit 10.